So hopefully you guys enjoyed the accidental 2 days off of lecture that we had. So hopefully you saw the email announcement that I sent out, but due to people not being able to get into campus or pick up their exam, I'm extending the exam regrade through end of lecture today. So if you got it on you and you still want to submit it for points or have me look at it, go ahead and turn it in at this table at the end of lecture. And then I'm going to go through them this afternoon or this weekend and hopefully post any updated scores in Canvas and then get them back to you guys in Monday's lecture, or failing that, parcel them back out to your TAs for distribution and recitation. Also, Chapter 7 Sapling's now open. I sent out an email about the deadline for Chapter 6 being extended because I completely neglected to set it earlier and a few people missed it. So that actually just closed a couple minutes ago, so we should be good there. But if you want to start working on 7, that's open now too. So, okay, so any questions about that or any other administrative stuff? All right, cool. All right, so what we were looking at way back a week ago, we are a little bit into Chapter 7, looking at cyclic compounds. Okay, so just to work quickly back through like an example of what we're doing here, for anyone who missed last Friday and still hasn't seen the lecture capture, what we're doing is taking some kind of top-down view of a cyclohexane, because cyclohexane is the most stable ring. We're going to be spending most of this chapter on it. And we're looking at how can we take something with bold and dashed bonds indicating stereochemistry, say something like bold methyl, dashed chlorine, bold methoxy. Oh, I guess I haven't covered the naming for these. We'll get to that later, but CH3O is called methoxy. And how can we turn it into one of its 2 chair flip forms? So as a reminder, we're going to draw 2 parallel lines. If they tilt up to the left, then you're going to have the lower one offset to the right just a little bit. And then a tip goes down at the left and up at the right. So if you've done it correctly, you should have about the same height level between those 2 points as between these 2 points. So that's one chair, and then the other one is up to the right. So you can draw the other shape of chair that way. Okay, so just following along with the same example that I did before. If you remember, when we do a chair flip, we're going to toggle which carbons in the ring are pointing upwards and which are pointing downwards. So maybe, say I arbitrarily label this one with a star. I could label any of them. This one's starred. I'm just going to pick, say, this one to be star because it's furthest to the right. Easiest to keep track of that way visually. But again, you can pick any one around the ring if you want. So here, in this form, the starred carbon is up pointing, which means after the flip, the starred carbon has to be down pointing. And then I can plug in the groups that are attached. Anything bold in this top-down view has to be up or slightly up in the chair view. So in this case, coming off of here is up, which means for an axial, for an up-pointing carbon, up happens to be axial, so it's going to be pointing straight up. Whereas over here, it's still up-ish, but now it's up equatorial. All right, so flipping between the 2 chair forms doesn't change which substituent groups are up or down. Like methyl starts up and it stays up the whole time. It's just toggling axial and equatorial. Okay, next one, chlorine is down, which happens to be down axial there and down equatorial there. Then we skip a carbon, and then OCH3 is up, which happens to be up axial here and up equatorial over here. Okay, so you can go around and double check, like everything that starts bold should be up the whole time. We're just flipping axial and equatorial. Okay, so any questions about that review? Yeah? CL or CH3 rather be on an equatorial? Good question. So that's actually sort of where I wrapped up in the middle of a topic last time. So I do want to say some more about that. So in general, like with a couple of really weird exceptions, which generally have to do with more complicated things like hydrogen bonding, which we can get into later, pretty much every group prefers to be equatorial. And so we're not going to get into details on this, but it turns out that every group has an associated what's called an A value, which is the cost of being axial, like the energy cost of being like up axial instead of up equatorial, for example. We're going to assume that the A values, like the cost in energy of being axial, is about the same for all groups. It's not completely true, but it's close enough for our purposes. So we're going to assume it's the same strength for all groups except one special case. Does anyone remember what it was that I covered like right at the end of lecture last time? Terbutyl, yeah. So terbutyl, you can show it as like a bond coming off of the ring with this crowfoot looking thing, or as a carbon with 3 methyls on it, CH33. But, so I guess, between these two examples, here I've got 2 groups axial, 1 equatorial. Here I've got 1 group axial, 2 equatorial. Fewer groups axial is better, so this conformation is more stable. So for the most part, we can treat it as just like a majority vote. 2 of them want to be equatorial here, which they can be at the cost of this one being axial. But as soon as terbutyl comes into play, the other votes of the other groups don't really matter anymore. So like, if we did pretty much the same 2 molecules just with a terbutyl group, and again, sorry I'm drawing chairs kind of fast, but just for demonstration purposes. Okay. So terbutyl axial versus terbutyl equatorial pretty much doesn't matter what the other groups are doing. Again, that's not 100% true. It might depend on exactly what numerical energy is associated with it, but for our purposes, we're just going to look at either terbutyl is axial and a couple of smaller groups are equatorial, or vice versa. Okay, so here we would expect like, okay, 2 groups axial versus 1 group axial. That's normally we would expect like 1 group axial being better. But because that 1 group is terbutyl, that's the only thing that really matters here. So T-butyl equatorial is more stable. Okay, so questions about that so far? Okay, cool. So in terms of why things like to be axial versus equatorial, I sort of showed that a little bit on that model kit I brought in a week ago, but we can actually use a tool that we've already played around with a little bit to explain it in ways that we've already gotten used to seeing. So what we're going to do is we can explain the preference for equatorial with sort of a fancier version of Newman projections. Okay, so let me draw at chair, I'm going to draw this one tilting up to the right. So like this. And I'm going to draw a CH3 sticking up off this back right carbon there. Okay, so if you remember Newman projections from chapter 2, what we need to do is pick a bond and sight along it. So what I'm going to do is look along this bond here that I'm shading in bold. But remember that chair cyclohexanes are made up of a whole bunch of parallel lines. So two opposite sides of the ring are always going to be parallel to each other. So if we're sighting along this bond, assuming that perspective is not a thing that exists, we're like in some isometric view here, then we're also at the same time sighting along this bond here on the opposite side of the ring. So what we're doing is we're going to draw two side-by-side Newman projections. So if I do numbering here, I could say like 1, 2, 3, 4, 5, 6. So the left half of the ring has 4 in the back and 5 in the front. The right half of the ring has 1 in the front and 2 in the back. 3 and 6, you'll notice those carbons aren't part of either bond that's getting sighted along. So those are shown as kind of bridging carbons between the two halves of the projection. So 3 we see kind of dips downwards, and it connects carbons 2 and 4. So I'm going to show a connection between the two back carbons there, dipping downwards. That's 3. And I'm going to sneeze. Nope. False alarm. Okay. And then carbon 6 connects the two front carbons, carbons 1 and 5, by sort of tipping upwards in the front. So note that I'm connecting them to the two dots that are the front carbons of each Newman projection. Okay. So that's the basic skeleton of what I'm looking at here. Any questions about that before I start filling it in? Okay, cool. Alrighty, so carbon 1, I have pretty much no groups of interest, but I can show the H's coming off of here. I'm going to show H down axial, up equatorial, which means coming off of carbon number 1, I have an H straight down and an H up and to the right. Okay, so any questions about how I'm doing that? Okay, and then in the back carbon, carbon number 2, I have sticking straight up my CH3 group. I'm just going to like draw a box around that so it's easier to keep track of visually because it gets a little crowded on here. And then I also have off of here an H that's down equatorial. So that's going to be showing like down and to the right there. Okay, and then I can do the same thing out on this carbon, out on this bond, only everything else coming off of there is just H's. So H, 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 and H. Okay. So the reason why we're incurring a cost for being axial with the CH3 is exactly the same reason that we've been seeing for like why some conformations are bad even if they're not eclipsing. And that is between this CH3 and carbon number 6 of the ring, there's a gauche interaction. And that's costing the energy. Okay. So that's part of it. Like this CH3 is automatically going to be gauche to this carbon here, carbon number 6. And if you look, we're sighting along this bond, 6 and the methyl group are sort of like rotated 60 degrees apart from each other. So that's one gauche interaction. The other one, I can't show looking at it from this perspective, but it's going to be between the methyl and carbon number 4, which is also pointing up. So let's draw a different sighting for that. Okay, so again, same chair conformation, CH3 is up. But now I want to look at the relationship for the other bond coming off where the methyl is attached. So I'm going to be sighting along here. And again, because they're parallel to each other, I gotta, at the same time, be looking along here too. Okay, and again, let me throw the numbers on there. I don't have them in the notes, but I should probably add them because they make it easier to keep track. Okay, 1, 2, 3, 4, 5, 6. So now my left eyeball is looking down the 6 to 5 bond, if you guys can see that. So 6 in front, 5 in back. And my right eyeball is looking down from 2 to 3. So 2 in front, 3 in back. Okay. Meanwhile, carbon number 1 is not part of either of those bonds, but it's connecting the front 2 carbons closer to my eyeballs, and it's dipping down in the front. So like that. And then carbon 4 is not part of either bond either, but it's sticking up, connecting the back 2 carbons. So there's 4. Okay. So questions about that? Yeah?
The 3 and the 5 in that case, and the 4 and the 2 in the other case, those are behind, and we can't see them. You're just putting them there to let us know, right?
Sort of. I mean, like in a Newman projection, they're the back carbons here. So like the 3 and the 5 here are just shown as like the circle parts of the projections. So. Yeah, but yeah, officially like one carbon is exactly blocking your view of the other. It's just like as a Newman projection, we got to show it anyway, and so it's shown as like a circle that's sort of, yeah. Okay, other questions about this so far? Okay, cool. So finishing this one up, so we know carbon 2 here has the methyl going straight up. So you got CH3 sticking up off of there, and then we can just fill in everything else coming off of the ring is just H's. So H, 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 and H. Okay, so again, here's our methyl, and here's the Gaussian interaction that's costing us energy. It's kind of harder to hold the methyl there just because it doesn't like impinging on the space that's taken up by one of the ring carbons here, carbon number 4. So in other words, this, the methyl to carbon 4, is another Gaussian interaction. Okay, so one common test question format that you might see both from me and in the exam archives from other people is, here's a chair conformation, show all the Gaussian interactions in this conformation. So in other words, having something be axial automatically gives it 2 Gaussian conformations, or 2 Gaussian interactions right off the bat. So if it's an axial group on an upward pointing carbon, it's going to have those interactions with the other 2 upward pointing carbons. So here it's up on carbon 2, and its 2 Gaussian interactions are to the up carbon 4 and the up carbon 6, in other words. Okay, so it is possible to get other Gaussian interactions. Oh, and I guess one last note about this is that the energy cost of having a methyl group specifically be axial is pretty similar mathematically to the cost of like a couple of Gaussian interactions in butane, which is kind of to be expected because it's more or less the same groups as when we were looking at butane, like a CH3 at one end and not quite a CH3, but part of a ring at the other end of the interaction. Okay, so that's one source of Gaussian interactions. The other one is if you've got 2 groups coming off of adjacent carbons. So I didn't leave myself enough room to draw it there. Hopping over to the other side of the board. So for example, if you have methyl that's down equatorial there and up equatorial here, neither of them is axial, so neither of them is Gaussian, having a Gaussian interaction with any part of the ring. But if we do a Newman projection sighting along these bonds again, we're going to see that okay, so I'm going through this example real fast, but hopefully you can sort of follow along based on the steps that we took over here, left as an exercise to the reader, I guess. Okay, so in this case, neither of the CH3s is having a Gaussian interaction with any part of the ring, but they are still on adjacent carbons and they're only 60 degrees apart from each other, so this would also count as gauche. So in other words, it's possible to have interactions between adjacent groups. So if I draw you like a chair conformation with like a bunch of methyls coming off, first of all, you would want to check, okay, like, do any of my methyls have like axial positions, in which case that's two Gaussian interactions right there. And then you would want to check, okay, if there's any groups that are next to each other, do they have Gaussian interactions with each other as well? And then that would add to the number of Gaussian interactions you've got. Sorry, was that a hand raiser? No, okay, sorry. Okay. Okay, so any questions about that? Yeah?
So, what do you should say that on any two adjacent carbons, if both are equatorial, they are not?
Yep, both being equatorial, or if one's equatorial and one's axial, it turns out to also happen. So basically, the only way to avoid having gauche between two adjacent groups is both be axial in opposite directions. So just one quick example of like one axial, one equatorial being a problem. If we do CH3 down here, down axial in the front, and down equatorial in the back. Now if we do the Newman projection here, we got H up, down, CH3 down in the back, and then, oops. Okay, so again, going through that pretty fast, but you can see that down axial is still going to be a problem next door to down equatorial. Okay. So yeah, the only way to avoid adjacent groups doing Gaussian interaction is having them both be axial in opposite directions, which then raises more problems because now they each have their own Gaussian interactions with parts of the ring. So sometimes there's no way to get to like zero energy conformation in these things. It's just trying to minimize the number of Gaussian interactions. Okay. So any more questions about this conformational analysis stuff for rings? Okay, cool. So, let's see. So we've spent a little bit of time on six-membered rings, which are probably the most important ones to know what's going on geometrically. We are going to spend some parts of this chapter on smaller rings, just real briefly, just to cover like why they're not as popular with molecules or not as stable. Okay, so smaller rings. So if you remember that table of energy values from the start of this chapter, you might have noticed that five-membered rings are not quite as good as six-membered, but they're not too far off. So cyclopentane's almost as good. So cyclopentane is almost as stable as cyclohexane. We're going to spend like a real brief amount of time looking at what shape it takes, and then that will explain why we're not going to dig too much further into it. So what this does is make an envelope shape where four atoms are in plane and then the fifth is sticking up above or below. All right, this is going to be a little tricky to draw, but so sort of look at a square like you're looking at it in perspective. Pretend it's an envelope lying on a table, and then there's like the flap of the envelope that hasn't gotten stuck down yet that's sort of pointing up out of plane a little bit. Or you could show it the other way, where it's like 4 atoms in plane and then the other one sticking down instead. All right, so the out of plane one could be above or below. The problem is that there's no set atom around the ring that has to be the out of plane one, like they all take turns, which means that any one of the 5 atoms around the ring could be out of plane, and it could be up or down, which right there gives us 10 possible conformations instead of just the 2 that we're looking at for chair cyclohexane. So it's not really that worth getting into because it's just too much to analyze and you don't really get that much useful information out of it. So 10 conformations that are lowest energy plus like a bunch of sort of in between ones as it's passing from one stable conformation to another. Sort of like when we were looking at Newman projections way back in chapter 2, we sort of have like gauche and anti-conformations as the stable ones, but we have to pass through eclipsing to get there. I don't think I actually talked about how we do the chair flip when, sorry, so I'm going to cut back just a little bit here and talk just a little bit more about chair cyclohexane because I think I skipped that last time. But if you remember the model that I brought in, when you're doing the flip from one chair to another, at one point we have so I take one corner and I bend it sort of in its opposite direction, and then eventually I'm going to bend the other one back up to get to sort of the ring flip form. I don't think I actually said the name of what this is called, but this is called boat cyclohexane. And we're not going to spend much time on it because the molecule never stays there for long. There's a lot of eclipsing stuff going on in this conformation. You can sort of mitigate how uncomfortable or how high energy that is for the molecule by sort of twisting the 2 corners just a little bit to like one side or the other, which is called twist boat, predictably enough. But again, we're never going to really bother drawing either of those because the molecule, it's just passing through boat or twist boat on its way from one chair form to another. So Loudon has this whole energy diagram of like it starts in one chair conformation, it goes up energetically through boat or twist boat, and then it drops down into the other chair. So really, these 2 are kind of the most important forms, and they're the lowest energy, although they might not be equally low in energy because depending on what's axial or equatorial, one form might be better than the other, but they are still both better than boat. Okay, any questions about that kind of doubling back side note? Okay, cool. Alrighty, so 5-membered rings have way too many conformations to be worth looking at too much, but they're pretty comparable to 6-membered rings in terms of stability. How about if we go a little smaller? All right, so cyclobutane Cyclobutane's a square. What are the bond angles going to be forced to be in that molecule? 90, yep, it's a square. So cyclobutane has 90-degree bond angles. Cyclopropane is a triangle, equilateral. What's its bond angles going to be? 60 degrees, yep. So just because of the shape that they're being forced to hold, they are not at all happy about what's going on in this ring. Because they're still part of a tetrahedral carbon, they still want to have bond angles of what for an sp3 carbon? Yeah, 109.5. Okay, so how do we account for this really huge discrepancy, like something that's almost half the size of the bond angle that we would really want to have? So this is creating what's called angle strain. Which is basically we're forcing the atom to have bond angles that are not exactly what it wants. It turns out this is bad enough that cyclopropane will actually compensate by not even doing straight bonds between the atoms. So bent bonds, or what some textbooks will call banana bonds. Okay, so in other words, if we show like carbon, 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 we're used to seeing, okay, sigma bonds would mean that we would have head-on overlap of this orbital, and they'd be centered along the line connecting the two nuclei, right? Turns out the lowest energy solution to this whole problem is not actually doing head-on overlap between the orbitals anymore. We're going to have like the orbitals kind of sticking off to one side, the outside of the ring. So they're not even like direct head-on overlap anymore. Okay. So it turns out at this point, the angle between the orbitals on carbon can relax all the way to 105 degrees. And I guess that's just the lowest energy point where it's sort of a compromise between, okay, carbon wants to get like good overlap with other carbons to make strong bonds, but also it really wants to be 109.5, and this turns out to be like the least bad solution to that. So we're paying for that with loss of orbital overlap. Sort of side-on-ish bonds are much weaker than the head-on that we would really hope to get for a sigma bond. So this costs orbital overlap, which means much weaker sigma bonds. And I'm actually not sure what the bond strength looks like, but I would expect it to be like probably not that much better than the strength of a pi bond, which we know are quite a bit weaker than sigma bonds. Okay, so this is why, if you remember the heatoformation table from the start of this chapter, cyclopropane is actually costing us energy to build it out of the associated nuclei, because it really is not happy about being crammed into this tiny little three-membered ring with a couple of other atoms. Okay, questions about that? Okay, cool. So cyclobutane is pretty similar, just to a lesser extent, because it's not being asked to do something quite so unreasonable bond angle-wise. Okay, so that's pretty much it that we're going to cover about smaller rings. We're not really going to cover larger single rings at all, because those also get pretty complicated in terms of conformations. But what we are going to cover for a little while here is things with multiple rings. So what we're going to look at now is bicyclics and polycyclics. Okay. So there's 3 different ways for rings to be stuck together. Okay. So one option is to have 2 edges. Oh, question in the back?
So, for example, wants to, if it like does the same banana like bending,
Mm-hmm.
will it be closer to 109.5 than the cyclopropane?
Yeah, my guess is probably like, yeah, I don't know like exactly all the factors that go into like where the compromise ends up falling, but yeah, probably like 107-ish, 108-ish would be my guess. Yeah. Okay. Good question. Okay, so the ways that we can stick multiple rings together, one option is we can just straight up stick one edge of a ring onto a neighboring ring, something like this. So maybe we stick a 6-membered ring onto a 4-membered ring by one of its edges. Do a few more examples of that. Maybe a 4 stuck to a 3, or maybe like a 3 stuck to a 5. Okay. So these are called fused bicyclics. Okay. So another option is we can do something that we've actually seen like 1 or 2 examples of. Actually, yeah, I guess a test question that I had about like what would the starting material of this look like, and then we did it for ozonolysis, sort of working backwards, and we had that weird like double bond holding it together across the ring. This is one example of that. So and I didn't expect people to draw it like 3-dimensionally back then because we hadn't covered it yet, but you could still figure out the connectivity based on what we knew. Okay, so here's one. I can draw it either this way, which I'll talk about in a second, or showing it this way as like just a top-down view of a hexagon, a 6-membered ring, with an extra 1 carbon holding it together across the middle of the ring. Easiest way to draw these is draw it sort of like a book lying open face down with like an extra spiny bit poking out the back. That's kind of closer to the shape that they adopt in 3 dimensions. Okay, another example is pretty much, I guess we could do the same thing, book lying face down with a spiny bit, but I'm going to erase this edge and instead do an extra carbon pointing downwards. So I could do that as a 7-membered ring with an extra bridging carbon. Okay, so I guess I sort of gave away a little bit what the name of this whole group of stuff is called, but this is called bridged bicyclics. Okay, so other than just eyeballing them, the best way to tell the difference between these 2 groups is figure out where your carbons are that are holding the rings together. So for example, here and here, here and here, okay. So what I've done is label what's called the bridgehead carbons. Okay. So the stars are the bridgehead carbons. And the way to tell for sure what the difference is between fused and bridged bicyclics, in fused, the 2 bridgehead carbons are directly bonded to each other. So you'll notice that my two starred carbons in this category always have a connection directly between them. That's the shared face of the two rings. In bridged bicyclics, they don't have a direct connection. There's always at least one other carbon in the way, no matter which path you take between them. Okay. So questions about the difference between those before I erase the board and then show the third example? Okay, cool. So I'll take a minute to erase this if you want to take a quick break. Uh-huh. Oh, whoa. Hi. Oh, sorry, what's up?
Break right now?
Oh, yeah, what's up?
Real quick.
Okay, so picking up where we left off. So the third category of ways that we can stick a couple rings together in our compounds. So I've seen sticking them together on one edge. We've seen doing this sort of weird bridged bicyclic thing. The other option is just having one atom in common. So I've actually seen some examples of this pop up. If you remember when we were looking at chirality without asymmetric carbons, this is one example of a system where the two rings are going to be like perpendicular to each other, where if we have like stuff coming off of one ring that makes it asymmetrical and stuff coming off the other ring that also makes it asymmetrical, we can have two different handednesses of ring systems stuck together that way. So these are called Spirocyclics. And if you want, you can actually show like explicitly that they're perpendicular to one another. One of them is going to be flat in the plane while the other is like coming straight out towards and away from you. Okay. So note that these don't actually have anything that would be called a bridgehead carbon, but they do have a central single atom holding the whole deal together. Okay, so we're going to look real quick at naming bicyclic compounds. Oh, and I guess spirocyclics are kind of weird. They're not actually considered true bicyclics, and we're going to name them just a little bit differently. Okay. Okay, so to name these, what we're going to do is label the two bridgehead carbons, and then we're going to count each of the 3 routes between them. Okay, and that doesn't include the bridgehead carbons. Okay, so for example, if we want to look at this thing, our bridgeheads are here and here. So if we follow one route, maybe let's go the left way around the molecule between them, we have to pass through 1, 2, 3, 4 atoms. So that's one route. If we go the right way, we have to pass through 1, 2, 3, 4 atoms to get there. And if we go the central way, we don't have to pass through anything. It's just a direct hop over. So that's 0. Okay. So what we're going to do is name this for how many total carbons it has. So this has a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms. We're going to name it as a decane, weirdly enough. We're going to call it bicyclo. And then we're going to put square brackets, and we're going to list the 3 numbers of distance in descending order. So we're going to call it 4.4.0. Bicyclo 440 decane. Okay, let's do another example. So just to list what we did there, that's descending order. How much time I got left? Oh, you know what? I'll cover another example in next lecture when we pick up here. Okay, if you have any exam regrades you need to get in, now's the time to do it, so bring them on up.